Okay, so in today's lecture, we are going to move on from supervised learning into unsupervised learning. So unsupervised. But this is completely a new module. So we have finished and supervised learning part, except for the neural network. That will be a complete separate module. So we are moving on the second module that is focusing on unsupervised learning. So the key of the unsupervised learning is the training data has no labels. So that means we don't know which class this and the data belongs to. We only have features. So the only training data that we have is all the features. And in particular for all of x is in R small d. So the key of this is, since we don't have any pre and assigned labels or values of the target, so the goal is we want to self-discover like patterns. So occurs naturally. In the training data. So this training data is basically our input. So there are basically two major topics that will be covered. One is clustering. One is like dimension reductions. So these are the two major topics that will be covered in this courses. We will spend quite a significant time on the clustering to introduce two main cluster algorithm. That is K-means and a Gaussian matrix. For dimension reductions, we will mainly focus on PCA. We will talk a little bit with something related to PCA, but it's called QDA and LDA. But this is more like a supervised version of like dimension reductions. Okay, so these are something that is extremely important. All right, so this will be the major overview of this and this module. And of course, this is not the end of all the unsupervised learning. There are a lot of other methods about unsupervised learning. Many of that will be covered in 593 and the other and TDA courses. But the focus of this whole courses in 592 is we actually need to implement these methods from scratch and understand all algorithm very, very carefully. All the math, all the derivations, and also all these and implementations from scratch. So let's focus on the clustering first. So basically, so a general clustering can be formulated as the following. So, the first is you're giving a data. You are giving all these unlabeled data samples. So basically we have a D equal to X of I from 1 to the N. So these are all the data that we have. Then, I mean, and obviously, I mean, it's unlabeled. That means we don't have any like Y's. And also we need to specify the number of clusters. Which is K. So the goal is we are going to group those examples into K clusters. So that means I'm going to assign each point for each and to each membership, which is that means each data has each cluster A, which is X of I, that it's either from 1 to the K. I mean, belongs to from 1 to the K members of the clusters. So, and also the only information that we actually have, so, and what we are going to use, I mean, information that we actually use is we only have similarities between data examples. So that means we're going to cluster those examples based on these mutual similarities. If two data point has high similarities, we're going to cluster them together. If two like data point has like I mean, and behave completely different, then so then I mean that will belongs to two different clusters. So how we actually measure the performance of the clustering. So so the whole idea is to measure the performance of the clustering. That it should and it should have a high as within cluster similarity and a low inter-cluster similarity. So that means within the cluster, they should have a high similarity. So high similarity within the cluster. And we should have a low similarity interclusters. Okay. So there are multiple ways to define the similarity. So like, I mean, obviously this is a very important and a metric before we actually start any kind of clustering algorithm. So usually similarity is inversely related to the distance. It's they can think about proportional to 1/over of distance. Right? So if distance is far and further away, then the similarity is small. If distance is small, then the similarity is high. Right? So this is like vice versa. So, and for example, if we have a Euclidean distance, and this is one of the commonly used distance between 2 points. So it's basically d of x of z. It's basically, you can think about using 2 norm of the differences between 2 and a 2 point. And of course, we have a talk about kernel trick you can use in kernelized distance if needed. So this d of x of z, it can be just, and basically we have some nonlinear mappings and map x and z into much higher dimensions, then we calculate the 2 norms. So this could be phi of x minus phi of z of 2 norm, but this phi is some like nonlinear mappings. Okay. And of course, with the different choices, it might give you different clustering and behavior. So that's why before you even study, you have to choose what kind of cluster and what kind of distance that we should be using. So, and also and not only we can and focus on with the 2 norm, we can and work with 1 norm as well. So like, and we can use Manhattan distance. So this is something that we just using the 1 norm instead. I mean, this is also a distance. I mean, the homework, you're going to work something like that. And to implement all these and the stuff from scratch. Okay. So these are all, I mean, all possible distance that you can choose. Of course, that's not the only one. But there's just some candidates. So let me show some different algorithm and what is the behavior of this and the clusterings. So right here, yes. So you can see right here. So, and as I said, like different like choice of distance will lead to different clustering. For example, if we have this and the data, we have an inner circle and outer circle. Can we split the data into 2 clusters? From eyeball, we know there should be a cluster into the inner circle and the outer circles. But in general, that would be a very difficult problem because like I mean, if data is in much higher dimensions, how do we know? I mean, this is actually give you the inner circle and the outer circles. And obviously, this is completely nonlinear problems because circle is nonlinear object. So that will be quite difficult to actually identify this as circle and classify them into, we have like 2 different size of circles. There are multiple algorithms that you can use. For example, this is like mini batch K-means. We have like an affinity and a propagation, mean shift, spectral clustering, DB scan bridge, and we are not going to talk about this in detail. Like for example, this like so agglomerative, like merative clustering and the spectral clustering. These things are, I mean, and DB scan probably being and discussed in TDA courses. We are also like, and we are also mentioned a little bit in, I mean, in 593 courses. But for this courses, we are just mainly focused on the K-means plus some like Gaussian mixture models that is not being discussed here. Okay, but you can see, and each of that has completely different behavior of of the clustering. So that means different models of the clustering also can make any significant differences. And rather than this like any distance that we have, we under those models and algorithm will also make significant contributions to the effect of the clustering. Just by looking at these and the behavior, you can see this DB scan actually behaved the best. DB scan can set and it can correctly so cluster all four and the clusters. For example, this one is inner circle and outer circle. This is 2 half moon, which is a very typical and a data set to be used to test those like clustering algorithm. This is 3 and the 3 dots. These 2 dots are close. The other dot is further away, so it can like classify very clearly. We have 3 dots. For this is completely uniform and like data set, it just classify. We only have a 1 cluster here. So you can see this is quite successful. Unfortunately, we're not going to talk about this in detail. I also have a separate class on like advanced machine learning, which covers this DB scans algorithm and implement them from scratch. Okay, but you can see this clustering is very subjective. It depends on, and not only depends on the distance, it also depends on the algorithms. It's completely non-trivial to say one partition is always better than the other. One way to see it, for example, for these data set right here, they have, and for example, these 2 clusters are quite close to each other, but it's significant, like further away from this cluster. So you can argue there are only 2 clusters. That means we have a cluster of these 2 blobs and another cluster and is much further away. All we can do is we have 3 clusters, and that means each blobs like belongs to and each individual like clusters. So it's very subjective. It doesn't mean like one has to be better than the other one. So it is it's up to it's up to certain applications. All right, so let's just go back to the notepad. Okay. All right, so that means, but no matter how you do, and each algorithm has 2 parts. So the first part is you need to define some objective functions. And so in each algorithm, so first thing is you need to define the objective functions. The second thing is you need to define the distance and the functions. So we have a talk about distance function already, but obviously different algorithm means we work with a different type of objective functions. So then we also need to design an algorithm to minimize the objective functions. So this is very similar in the supervised learning. So we have some loss functions, which is our objective functions. And we are going to design some algorithm, could be gradient based or non-gradient based, like and decision trees, to actually minimize these objective functions. Okay, so these procedure is very, very similar. And in fact, almost all machine learning data science problems, this is always like that. So this is quite universal. All right, so let's just talk about the K-means class and the clusterings. So for example, let me just see like 2 versions. And we need to define and what is the objective function, right? So if we have some black point right here, we have some red point right here. So naturally, you would think I want to build a cluster one right here. I want to build another cluster right here, right? So it will be a bad idea if we want to say, I want to build a cluster right here. Why? Because those data within the same cluster in this blue cluster will have very very low like similarity, because this point right here and this point here, the distance is very hard. So technically, I would say, to be clustered with the black and the red is more reasonable. It's just because so it will satisfy this, our measure of performance for the clustering that is high similarity within the cluster and the low similarities interclusters. So this is the general rules of what we have. So basically, if we want to have a smaller within cluster variances, so the key goal is I want to have a smaller variances or smaller sum of and the sum of distance and square distances within cluster, smaller variances within the cluster. So that means if I want to say this belongs to the cluster, so that means if I want this to be x of I belongs to, I want to say it's the mean of the cluster. So mu of j, sum of all my xi belongs to this cluster j. I want to sum all of the square of the distances. So this is basic says this is equal to the cardinality of the members in this cluster, Cj, times the variances of the Cj. All right, so basically the variances is basically and the subtract mean, then square of the distances here. And also this mean right here is defined as following. It's one of the cardinality of Cj of sum all of the positions of the member, and which is basically the mean of the positions. So these are all vectors. So this is just basically we want to minimize all possible situation that to minimize the variances between the clusters. So this is a quick summary or quick overview of what we're trying to do here. So let's just be more formalized and let's see how this actually work out with very specific, so in terms of K-means algorithms. All right, so in K-means, so let me just repeat our input. Input is all these data D, which is x of I, I from 1 to the n, which this whole thing is, and each data is in R little d, and the numbers of cluster K. So for the K-means, cluster K has to be predefined, right? In the next lecture, we're going to talk about how to using some algorithm to determine what is the optimal K. So and I said the distance, right? So we need to define the distance. Distance, we are going to using the Euclidean distance, which is commonly used, DEAN. So, and also we need to not only define the distance, in this case, we need to define the cluster. So, and basically the cluster C and CJ is actually a set of X of I. So like, and it belongs to this cluster J. Right, so for all possible of X of I, that belongs to the cluster of J. And also we define the mu of J, which is I think I'm giving right here is 1 over the number of CJ summation and basically the average positions for those and for those member points. So this is, I'm going to call the centroid. So you can think about this as being the means of this and the clusters. So this is called centroid of the cluster. All right, so the number 3 is we need to give objective functions, right? So the objective functions is we want to find out the K cluster. The goal is to find C1, C2 to CK, and also their corresponding centroid, which is mu1, mu2 to mu k. So these are the centroids. To minimize the total and the total within variances. To minimize total within cluster variance. So basically this objective to say it's we have summation X of I in CJ and we just copy and paste what we already have of the mu J square of the Euclidean distance. Then we sum all possible J from 1 to the K. The way that we do it is we want to minimize and we want to minimize. So the variable right here is the and the CJ and the mu J, right? So we want to minimize the CJ and also, mu J is basically the mean with respect to that. So in this case, is if we stack all these mu together, so and we can define this gigantic all the centroids And together we can stack them together. So this becomes mu1, mu2 to mu k. So this is actually an D by K matrices that we want to find for all the and the positions for all the centroid. Okay, so this is obviously quite important. So this loss function is called, and also called and a distortion here. So here we are still using a bunch of the and a bunch of summation here. So so this distortion actually has a name called J. I'm going to call it J here. So we can vectorize everything. So if we actually vectorize everything, it's so like vectorize it, right? This distortion here. So that means we are not using for each data entry X here. We're trying to using all the X like and the matrix here. So we have X right here. Subtract to Z. Then multiply the mu transpose. Wait. Yeah, I think D by K. D. Okay, so this is K by D. Yeah, this is K by D. So this will be mu. Okay, so then, so let me just like correct this part. Okay, so to vectorize it, so this becomes like, and here we are using Frobenius norm, square of the Frobenius norm here. So X here is the data matrix X of 1 to X of n. So this Z matrix is just purely the assignment. That means just tells me which cluster it belongs to. It's all 0 and 1s in n by k. So this is, for example, this Z is basically Z1 to Zn is the one hot encodings for those membership. So for example, if we assign xy into like cluster 2, so this Z1 will be one hot encoding of this class 2 in the total membership of Ks. So this will be 0, 1, and 0, 0, 0. This is in RK. So basically this is a one hot encodings for cluster of 2. So this is, the way that we actually vector and vectorize everything. So this we have, and we need to minimize the mu, and also we need to minimize the Z here. So this is something called distortion. But this is, so basically the same thing, just an vectorized version. The last, we also need to make a predictions, right? So because we need to, if we have the old data or new data, we also need to and make predictions to which and a cluster it should belongs to. So, I mean, although this is not quite obvious, but this is also very important in clustering. We also need to make predictions. So predictions and to assign those data to the cluster with the closest centroid. So, and assign this X right here, and which could be new, to clusters with the closest centroid. So what does that mean? It's basically the member of the and the cluster is arguing of all these clusters from 1 to the k of my X subtract the mu of C square of 2 norm. So basically we go through all possible mu and mu1 to mu k, and to find out which and the centroid is closest, and then that will be your membership. So this will be your membership. But one of the issue is this whole thing is very hard to like optimize. It's I mean the whole idea is I mean very hard to find the derivatives. So that's why this is not an easy kind of process. So what we usually do here is we're going to rewrite this an objective function a little bit and solve by the method called like alternative and optimization methods. So here it is the idea that here, and I want to remind you my J right here. I'm going to like and copy my objective one more time. My objective is J equal to, I have a double sum. That is summation J from 1 to the K, summation Xi in the Cj, X of I minus mu J square 2 norm. So I'm going to rewrite this into following, which is equivalent, but it's much easier to handle here. So this is equivalent. J is equal to summation. Because I mean the major difficulty is we need to find out Xi in the cluster of X and Cj. But that whole thing is very difficult to handle. So we are using indication functions or indication variables. So that I from 1 to the n, summation J from 1 to the K, this Rij, summation of Xi minus mu J square of 2 norm, and this Rij is indication variable, where Rij is equal to 1 when Xi is equal to Cj, is 0 otherwise. Right, so this is basically a simple rewrite of this whole objective function. There's nothing new here. So then what I'm going to introduce a method, it's called Lloyd algorithm. And so I believe you have seen this in the TDA class. If you took the and a recent version of an TDA, it's loyal algorithm. So the key idea is called like an alternative optimization, because I mean things that we want to and minimize to find is the R and the mu J's, right? So this is basically these two things that we trying to minimize. We want to minimize the Rij and the mu J. So these are the two things that we're trying to minimize. So this whole idea is called like an alternative and optimization. So the key here is actually you fixed one and trying to optimize the other one, and the vice versa. You do this alternatively. So this whole idea is very similar to the pathwise coordinate descent, and you have seen this in the Lasso algorithms. So it's very similar to Lasso, but I mean instead of we do this for each coordinate, we do that for like two different variables here. Okay, so let's just state those algorithms. So the step 0 is we need to initialize the mu J. So this part is quite crucial because if you don't initialize well, it might be stuck to some end result that you are not really and satisfied with. In the next lecture, we're going to talk about how to initialize this mu J smartly. And for now, let's just say we just randomly pick, this mu J's on the phase spaces. The whole spaces that we pick like k random points. Now step 1 is, as I said, we need to an alternative optimize the mu ij and rij and mu j. So the whole idea is fix mu j and minimize rij. So so what does that mean is we need to solve an inner. So this is basic says my mu j is fixed. My mu j is fixed. Only thing that we need to do is we trying to find rij here. So you're going to show in your homework that this process is equivalent in homework. Is finding the nearest. So I'm not going to complete this argument or prove it because you can do it by yourself. Finding the nearest centroid for each x. So i.e. you can, and this optimization, it's equivalent to say we're going to find rij according to 1 or 0 if j is actually the argument of this k of x of I and the mu k. So this is basically making the predictions right here. 0 otherwise. It is basically saying I'm going to assign this xi to the nearest centroid, which I'm going to assign this membership to the x of I to the nearest centroid, right? So that means this is basically saying we just make the predictions based on this mu j that you got given. Then intermediately, so that means you have a new membership for each of the data of xi. So that means you can update the cluster here, which is Cj equal to all of x of I when my x of I is in the cluster J. So you find and group all these xi that and it belongs to the cluster of J for all J is 1 to the K. So that means after step 1, you can update your cluster because you already assign each point to the nearest centroid. That means and assign the membership for each of the point. Then step 2, we are going to do this whole process alternatively. That means I'm going to fix Rij and minimize over mu j. Okay, so that means and we do this alternatively. So in the homework again, you're going to show this. This is basically and basically an update the centroid accordingly to mu j is equal to Rij x of I and divided by Rij. So you can prove this that we actually update this centroid mu j accordingly. So you solve this optimization problem, it's equivalent to say we update the centroid accordingly. So this is basic says, and this is also equivalent with we actually calculate the mean of each clusters. Cj. So what does that mean? So we have a mu of j. We just simply have a new cluster of Cj after step 1. Then what we do is just we calculate and recalculate this mu j based on the cluster. So this is 1 over number of Cj. So this is basic says if we sum all possible I for Rij and for fix of j. So this is basically the number of members in the cluster of j. So and this is basically our indicator variables that just indicate this has to be x of I in the Cj of x of I. Right, so that basically we calculate the mean of the clusters. Then step 3 is we go back to the step 1. Until some stopping criterion is met. So this stopping criterion is usually this mu j, and after this like step 1, step 2 iterations doesn't change too much. So basically it's a fixed. So so after my iterations, my mu j doesn't change at all. So that means there will be no more update, and I will stop my iterations. Okay. All right. So there are some important factors about this algorithm. In fact, for now, we are not going to prove any why this will work, but we were going to talk about this in the when we talk about and the Gaussian mixture models. So the key here is K-means here is a non-convex optimization problem. So because this objective function right here, it's usually non-convex with respect to mu j and Rij. So you see something like indication function, you have some idea this is like very likely to be non-convex here. But the important part is this Lloyd algorithm is the descent methods. So that means my distortion value will be monotonically decreasing during iterations. So that means it will always converge. It will always converge to somewhere. But our objective function is non-convex, so that means we might have a multiple local minimums, a lot of like other local minimums. So we might end up with just converge to some like local minimums rather than global minimums. And also, so if my objective function will remain unchanged when step 1 and step 2, and it doesn't change this cluster assignment, that means our algorithm is converged. So that means this my Cj and mu j are fixed anymore. As I said before, it might not converge to the global minimum. It might get stuck at some suboptimal local minimums. So so that means it's very sensitive on the step 0. So that means your result will be sensitive to the initial conditions. So that's why it's important to run your algorithm many times to get different version of distortion values. In practice, you can use the 10 randoms like restarts with a 10 random different initial values. So this ensures and you have more and a better chance to get smaller distortion values for different initial values. So this is very important because it might get stuck in some like local minimum here, but turns out my global minimum is much lower here. So you should always using this distortion values as a golden standard. You restart with the 10 different initial conditions at random. Then you compare the final distortion values. You need to pick and the result with the lowest distortion values and out of this 10 random starts. And of course, here we just assume this mu and step 0 is and mu j is chosen randomly. In the later of the next lecture, we're going to talk about the methods actually trying to choose this initial condition relatively smartly. This can ensure this whole procedure will be more efficient. Then you have a better chance to converge to the. Then you have a better chance to converge to the global minimum, rather than here and right here you just keep doing 10 random restarts here. All right, so but that's in the next lectures. So let me just illustrate with this graph right here. So say, this is my data set right here. I have, obviously we have 2 clusters, but let's say we just initialize with these 2 initial conditions. One one of mu1, will be here, which corresponding to cluster blue. This will be corresponding to cluster of red. And what you do is you assign all these points that is close to this like blue cross to be blue cluster, and everything that is close to this red cross will be assigned to be red cross and clusters. So now your cluster blue is like this, and this is your cluster red. And the next what you do is you are going to do this alternatively. So this is assign the membership, which corresponding to the step of 1. On the step 2 here, we are going to recalculate this and centroid based on this updated and the clusters. So now my new and centroid of my new cluster will be right here for the blue, and this will be my red. That belongs to the new centroid of the like cluster of red. So now you have these two centroid. Then you like redo things again to assign the clusters and to assign the points to the like nearest centroids. Now this becomes your blue cluster, and then now this becomes your red clusters. So you keep doing this alternatively until it start to like stop updating. And you can see right here, maybe after a couple like 3 or 4 iterations, this centroid start to converge to this point and then this point right here. This clearly separate my data into this blue cluster and the red cluster right here. So you can see this whole performance is quite well. I mean, it actually fits our intuitions very well. Is like successfully and separate this and blue cluster and the red cluster right here by randomly choosing these 2 initial conditions right here. But of course, this is not a guarantee. If you like re-pick your initial conditions, it's very likely it might get stuck at some other points. And here we are being lucky. We successfully and like cluster and cluster well. But in general, what you should do is you should like have a 10 random starts with those and with those like random initial point of the mu and a mu red and the mu blue. Then you run this 10 times to see which one has the lowest distortion values, which is our objective values. Then you're going to pick the corresponding one as our optimal and the clusters and our assignment to the memberships. All right, so this is the theory. In the next part, we're going to talk about the codings.